In this video, I will show you how to determine the standard enthalpy of fusion and the standard enthalpy of vaporization. In another video titled How Does Equilibrium Constant Depend on Temperature, we derived this equation. Assuming the standard enthalpy of reaction does not change with temperature, given a small or moderate temperature change. For endothermic reactions, the standard enthalpy of reaction is positive, and then this part is negative. When T2 is greater than T1, this part is negative, and overall, the value of the right-hand side of the equation is positive. Therefore, we know this equilibrium constant at the higher temperature T2 is greater than the equilibrium constant at the lower temperature T1 for endothermic reactions. Now we treat fusion and vaporization as endothermic reactions, and I'm using water as example. In the fusion of water, the reactant is pure ice. The product is water in a solution with a mole fraction x. Therefore, the equilibrium constant is x over 1. 1 is for pure ice. We get x. Vaporization, we have this water in a solution on the reactant side. On the right hand side, it's the standard state of water vapor, and therefore the equilibrium constant is 1 over x. And then we will replace this KEQ with x. For fusion, we will replace KEQ with 1 over x for vaporization, and then we have these two equations, 1 for fusion, 1 for vaporization. Because KEQ equals 1 over x, we have one additional negative sign here. We can set x1 to be 1. That's for pure water liquid. And then we replace this equation with simply the natural logarithm of x by replacing x2 with x equals negative standard enthalpy of fusion of R times 1 over the melting point of water in a aqueous solution with mole fraction x minus 1 over the melting point of water. What kind of water? This asterisk denotes pure water. And for vaporization, same equation, except that we need to replace fusion with vaporization. We need to remove this negative sign. Again, these two negative signs cancel. And then we need to replace every melting point with boiling point. And again, this is the boiling point of pure water. Again, since we are interested in the standard state, we're going to use the standard 1 bar vapor pressure to compute the enthalpy of vaporization here. How about melting point? Melting point does not really depend on pressure, only because the molar volume change in a fusion process is negligible. Now, in an aqueous solution, so let's say x is less than 1, we can observe and compute the melting point depression and boiling point elevation given the value of x. We simply plug in the value of x here and here. And we notice that the natural logarithm of x is negative, so this is negative. This is also negative. And then because of the negative sign here, and then we have negative value here, therefore this becomes positive. When this becomes positive, Tm is smaller than Tm asterisk. We observe melting point depression. And then again, this Lnx is negative. Therefore, 1 over the boiling point of water in a solution is smaller than 1 over the boiling point of pure water. And therefore, this Tb is greater than Tb asterisk. And then we observe the so-called boiling point elevation. Experimentally, we can simply add a very small amount of non-volatile, non-electrolyte in water and measure its melting point and boiling point of water as long as this x is close to 1, and then we can determine the enthalpy of fusion and enthalpy of vaporization easily, because we know the melting point of water is 0 degrees Celsius or 273 K. We know the boiling point of water, pure water, in the standard state is roughly 99.6 degrees Celsius or 373 K, and we plug in those numbers, and then we simply measure the melting point and boiling point of water in that aqueous solution. And if we know the number of moles of the non-volatile, non-electrolyte, and the number of moles of water, we can easily compute the mole fraction of water. So if we just plug in the value of the mole fraction of water and the melting point of pure water, the boiling point of pure water, and we plug in the values of Tm and Tb for the water in an aqueous solution, the only variable in this equation is the standard enthalpy of fusion. The only variable in this equation is the standard enthalpy of vaporization. And again, we're just simply plugging all those values and obtain the value of the standard enthalpy of fusion and the standard enthalpy of vaporization. If we have multiple data points, we can plot this natural logarithm of the mole fraction of water versus the reciprocal of the melting point of water in an aqueous solution. The slope multiplied by negative r will give us the standard enthalpy of fusion. Same here, if we plot the natural logarithm of the mole fraction of water versus the reciprocal of the boiling point of water in such solution, we will be able to obtain a slope. The slope multiplied by r, in this case there's no negative sign, we will get the standard enthalpy of vaporization. Now I will explain a little bit here non-volatile. This is because we want to measure the vapor pressure of just water on top of the aqueous solution. So we want to make sure the added substance has a negligible vapor pressure. Non-electrolyte, we do not want to have this foreign substance to change the enthalpy of water in the liquid phase. If we add electrolytes, usually the electrolytes will stabilize water by reducing its internal energy and enthalpy. And also, we want to make sure this X, the mole fraction of water, is not only less than 1, but also close to 1. So I say 80% or 90% of water. This is to ensure that each water molecule in that solution is surrounded mostly by just other water molecules. We're not trying to change the chemical environment for each water molecule. Again, the goal is to minimize the interaction, the attraction and repulsion between water and the foreign substance.